Hi. So we'll wait for a couple of minutes till others join, and then we'll start the session. Till then, if you have any doubts, you can let me know. We can uh, at least note the doubts down. Hi. So I think today is low on attendance, but if you have any doubts, I'll first take out the doubts, and then I'll move on to the uh, content that I have prepared for the session. Am I audible? Uh, no doubts on this side. Okay. I'll wait for a few minutes because if someone else joins and they have some doubts, then we will have to, yeah, we'll just wait for from 5 to 10 minutes, and then we'll move to the. In fact, till then I actually have a small question. Uh, so this was actually covered in the the batch normalization part of the this week's videos, and Sir posed a question that how do you perform the batch normalizations for CNNs? And he kind of left that as a homework problem. So maybe if you want, you can answer that, or give it a thought for some time. Oh, okay. You have not attended, in the sense, the video lectures. Okay, okay. So, okay. So, would you like me to cover the batch normalization concept till then? Okay. Yeah. I mean, since nobody's here, we can actually pass some time with this. So there were a couple of things that were discussed, but we'll first go in the general setup for training of any type of deep learning model. So usually when we are training let's say CNNs, or even classical neural networks, fully connected neural networks, or even as this week's content was, like, let's say for sequence to sequence data, sequence to sequence models like RNA STMs. In general, what happens is that if you I will actually bring it to a much simpler problem before we jump into the deep learning part of the problem. Let's say you have a output is equal to some a times input 1 plus, so maybe I will write a1, a2 times input 2 plus a3 times input 3, and so on. So I have, let's say, these three features: input 1, input 2, and input 3, and they together determine my output. Okay. So in general, when I'm trying to find these coefficients, so the goal of my machine learning model is actually going to be how the output depends on these input features. Okay. So when I have such kind of a setup, if for some reason one of the features, let's say in this particular case, let's assume that the input feature 2, let's say its values are way higher than input feature 1 or input feature 3. Okay. So let's say, just for an example, for a particular training data point, let's say the input feature 1 has a value of 2, input feature 2 has a value of, let's say, 100, and input feature 3 has a value of, let's say, some small value, maybe 0.5. Okay, and the output feature, let it be in the orders of more close to the orders of input feature, let's say, and something like this. Okay, in this case, if we wanted to find this a1, a2, a3, the coefficients, actually what could end up happening is that over, let's say, uh, over all the data points, this is kind of the trend. So your output feature is also of a very high, in fact order of magnitude if you look at it. So the input feature 2 is of the order of magnitude of output feature, the output, but input feature 1 and 3, let's say, they are not of the same order. But in general, you would want all of your model to consider all of the input features. So it should not completely base its prediction only on the input feature 2. Okay, so if you wanted that, but your data was of this sort, that the input feature 2 was closer to the order of input feature, the output, but the input feature 1 and 3, they were of a lesser order of magnitude, or in general for any number of features. So what could happen in end up happening in such a scenario is that your model will try to associate the fact that only input feature 2 is the main thing that determines the output, and it will kind of put more weightage on only understanding this A2 relation. Okay, so that is the reason why over your entire training data, you try to do something called normalization. So the idea of normalization is that you will take all the values of input feature 1 in your entire data set, and so let's say you had for the first data point the input feature 1, so I'm going to put 1 at the top to denote the data point, number maybe, and 1 at the bottom for the feature number. Okay, so if for the first data point, so x1 1 will denote the first feature's value, and x2 1 will denote the second feature's value for the first data point, x3 1 will denote the third data points, third feature's value for the first data point. Okay, and similarly you have all the data points. So for nth data point, you would have x1n, x2n, and x3n. Okay, so far is the setup clear? Okay, so now what you try to do in normalization is that you essentially take all the over the entire data set. If you are doing the normalization over the entire data set, you take the first features values for all the n data points in the data set, and you try to find the mean of that. So you basically will take x1 I, and from that you will subtract the mean over all the so mu x1 is actually denoting the mean over all these values. Okay, so I'm going to replace each of the data points values. So x1I, I'm going to replace it with x1I minus mu upon sigma square x1. So I'm normalizing the first feature values for all the data points. Okay, is this making sense? Yeah, so normalization will essentially so if if the actual values were all in this range, so 2, 3, 4, 1, 1.5, something like that, it would still keep it will bring actually everything on a distribution of this sort. It will make it into a distribution, a Gaussian distribution in fact, with a zero mean and unit variance. So doing this operation actually makes that happen for all features. Yes, so first we did for the first feature, we'll do it for the second feature also, for the third feature also, and you will in fact reformulate all the features, and then you again have a set of data. So this x1 feature has now been reformulated as in this form. X2 feature has also been reformulated in the similar form. So that would be like something like x2i minus is equal to x2i minus mu of x2 upon sigma x2 square. And similarly you do it for the third feature also. And now you would see that all of these values, they are in a closer range, so they are not in the once you have subtracted this, so let's say all the values of x2 feature were 100, 200, 150 of those order, but all of these values were of much lower order, in fact 2 order of magnitudes lower. So doing this operation would ensure that they are all in a similar nearby range, and when you train a model and try to find this a1, a2, a3 from those as inputs, you would end up getting, in fact you will normalize this guy also, okay, so output also will be brought in the similar range, and all of that will ensure that you would not put more weightage on only one of the features. It will have all the features being weighted equally. Okay, so now once we have done the normalization, so in general when you are training some like a complex model of this sort, your data is not just, let's say, 3-dimensional. In CNNs, if you have an image of, let's say, some 100 cross 100, so that is already 10,000. So the feature size, the input size itself is very big. So what you do in case of CNNs and stuff like that, you would process the data in batches. So let's say I have let's say 30,000 images in my data set, and each of them are somewhere 100 cross 100. So as you can see, the number of inputs numbers that I'm churning, that's in a very high order, right? So it's 30,000 times 10,000. That's already a very, very big number. So the input numbers that you are going to churn, that's going to be a very high order number. So we don't want to do that, and you can't. This 30,000 is the dimension. No. This 30,000 is the number of images I have. So for CNN, that would be the number of data points. So I have 30,000 images, and each of those images 100 cross 100, let's say. Then I would have this would be the number of the amount of numbers that I have to churn basically while training. But in general, we can't load all of these numbers at once into our let's say computer's RAM. I mean, it will directly overflow, and you don't want to do that. So what you do is you will take these 30,000 images, and you would, let's say, group them into batches of 30, let's say. Okay, when you say features, it will be 100 cross 100 for each of 30,000. Yes, I mean I'm talking right now the input image itself. So these are not, I mean, in a sense you can say them as features, but for an image, it itself is the feature, right? So let's say this image had something, I don't know, maybe a face of a person, something like that. So this entire thing, let's say, is 100 cross 100 pixels. That is what a CNN would be having as the input, right? So there are, let's say, 30,000 such images that I have. Each of them are 100 cross 100, and that's a huge number of numbers to churn. So when training such a model, I would ideally want to not load all of the images at once into my RAM. I would try to load few at a time, and that's why I'm saying, let's say I'm loading 30 images at a time. So I have batches of size 30. Okay. So how many batches would I have? Thousand, exactly. So I would have 1,000 batches, and each of them will go one after the other, and that will be used for my training. Okay. So I will send in batch by batch of 30, do my processing on those, and update my weights, and I will train my model. Okay. So when we are doing this sort of thing, the normalization that we perform, since we have not loaded the entire data set at once, we can't normalize using like this. So here we had all the features of all the data points at once. Here we had the availability of all of them, but since I am loading in batches, I only have 30 at a time, 30x1, 30x2, 30x3, something like that, right? So the normalization procedure that we do in that case is the batch norm. Okay. So are you getting that term now? Yeah. So in the content of the week, sir explained how you do batch normalizations for, let's say, classical neural networks. I'll briefly cover that, and then I'll pose the question for CNNs also. You have completed the CNN part, right? From the previous weeks. But we need the overall normalization. Yeah, I mean, ideally you would want to do that, but since you can't load the entire data set at once, this is the next best thing that we can do. That's why we are doing batch now. Okay. So let's consider a neural network which has 4 input features. CNN pending. Oh, okay. Okay. Okay, that would be a problem then. Okay, I will try to cover as much as, yeah. Okay. I'll try to cover whatever I can in this then. I'll give you only a sort of a very brief overview of what CNNs do, but I mean, I can't cover all that is happening in the lectures. I mean, you would need to go through those if you, I mean, to understand it in much details. Okay, so I'll first cover what batch norm for a neural network works, how the batch norm for neural networks works, and then we will go and look at CNN theory a bit. Okay. So let's say you had some sort of network like this. So this, let's say this was your input layer, and let's say this was your output layer. So you essentially want to, for example, it might be a classification problem, and this output layer might be denoting the probabilities of a particular so this particular set of features. Let's say these are your x1, x2, x3, x4. Okay, so you have 4 features and you want to, let's say, classify it into 3 classes, and the first number is actually denoting, let's say, the probability of this input that came in the form of 4 features, it belonging to class 1, class 2 or class 3. Okay, so your final prediction will be based on whichever one of these is the highest. So that could be one way. Okay, so the probability of it, let's say, being from class 1 ends up being the highest, you would say that this particular input of 4 numbers represents something that belongs to class 1. Okay, in general, when you want to do some sort of this thing, let's say you had a hidden layer in between here. Okay, you take these 4 inputs and each of them are going to be passed to each of the neurons in the hidden layer. Okay, what is the purpose of hidden layer? Okay, so are you also yet to complete the neural networks? Okay, just a general question. Okay, so I mean, introducing a hidden layer would increase the complexity of the model. That's the main idea. So if you didn't have any hidden layers and you are simply trying to map from inputs to outputs, that would not give you, yeah, that's what it signifies, a method for us to increase the complexity. So the classical linear regression operation, if it had been W transpose X equal to Y, so where X was your inputs and some weight matrix that as we saw before. So this is actually your similar to what I was showing just above, A1, A2, A3 and X1, X2, X3, and you keep having it for all the features, but you want to find that general A1, A2, A3 which works and gives you the correct output for all input X1, X2, X3. And this is equivalent to this. So if that would be a normal linear regression, but when you introduce neural networks, you don't include just W transpose X, you try to add a non-linearity on top of it, and when you introduce multiple layers, the output of this layer, which is already imposed with a non-linearity, and all of these inputs. So all of these inputs that added up to give W transpose X for this particular neuron, and to that you added a non-linearity, which something like a sigmoid function or a ReLU or some sort of non-linearity. And when you, so similarly you had that non-linearity added on all of them and their corresponding W transpose X, and all of that went into this guy, and again here you did weights times all of these inputs to get you some number, and again non-linearity on top of that. So maybe this I should call something different. I will call this H, since it's the hidden layers neurons values. Okay, so as you can see, we have added a complexity, right? So maybe I will call this W1 transpose X times W2 transpose, so because of the second layer, and this, so this entire thing which came here was the input to the next thing, along with the other neurons inputs. And on top of that you added a non-linearity. So you can see that you increase the complexity of the model by introducing this. Is this part clear? Okay. So yeah, I mean, if you increase the number of hidden layers, you can keep on increasing the complexity of the model. Each hidden layer will add more of these W's for you to train, basically. Okay, so where were we? Yeah, I was trying to tell batch norm. Yeah, so when you are working with batch norm for a neural network, let's say one of my batches was, let's say, as I had above, some 30 inputs, so 30 data points in one batch. And I had 1,000 such batches. So whenever I get one batch as the input, what I'm doing is I'm getting actually 30 of these x1 values, similarly 30 of these x2 values, 30 of these x3 values, and 30 of these x4 values. I'm normalizing these guys with respect to all those 30 values, and then passing those as the inputs. Okay, and you can do the same thing over here also. So after passing through here, you will again, for each of the images, each of the input data points, you have 30 times passing through this. 30 times you are passing to this guy. Okay, it's becoming nice. Okay, so you can keep doing the same procedure and ensure that for every successive traversal through the layers, it always has this feature balance happening. Okay, is that making sense? Prior to sending to the next layer, yes. Okay, so now the question was actually, so sir actually posed this question in the class, that if this is how you do for a classical neural network, how would you do it for a convolution neural network? But we need to first go through some theory of CNN also, I think. So, fine. Okay. So CNNs are actually for us to process image data. How much of an idea do you have of CNN? I mean, do I need to cover the entire thing or some specific portion? Oh wait, not seen any lectures yet. Okay. Okay, I will try to keep it short, but I will just try to give a very brief overview because it would take very long if we try to go into all the details. So, in case of CNNs, we'll first motivate why there is a separate class of networks if you want to process images, okay, instead of neural networks. So as we saw, so let's say even if I had a 100 cross 100 pixel image, but even in your phone camera, if you look at it, it will actually be a megapixel image. So in fact modern phones it will be even more, something of more size, but in general the size of the image, so you can't work with something of 10,000 dimensional space, or even if you have a megapixel image, 2 more zeros. So if you keep on working on an input size of such a big size, your neural network would not train well. I mean, there are way too many inputs and way too many things to train, and the number of parameters required will grow way too much. It will go very high. So to solve this problem, you do something called a convolution operation. Okay. So what you essentially do in a convolution operation is that, let's say I'm zooming into a small part of the image. So let's say I'm zooming into this upper corner, okay, and it has a 3 cross 3 size element, okay, and let's say for now let's consider a grayscale image, which means there is no colors, okay, only black and white, 0 or 1, yeah. So it's only in one dimension and there are only 0 and 1s, okay. So if you had something like that and you are working with that, let's say the image was of this type, okay, this top corner part of it, okay. What you not first cell, I'm taking first 3 cross 3 cells, okay. So what we try to do with convolution operation is that you take something called a kernel, and this kernel is also actually in very often cases it's actually another 3 cross 3 set of numbers, okay, and that corresponds to your sort of the W part that you saw in the with the weights that you saw in the classical neural network. So this also has a set of this also had a set of numbers which you are going to try to train, so that when I pass, so what I will do is I will take this, put it on top of this. I'll take this 3 cross 3 grid. I'll put it on top of this. Take element wise multiplication of all the inputs. Okay, so I will multiply this number with this number with this number with this, and so on, and then I will add them all up. Okay, so that is actually the convolution operation. Okay, and then I will take the same kernel, same 3 cross 3 grid. I will take it and put it onto the next 3 cross 3 or the adjacent 3 cross 3 grids of the main image. So I'll try to make it a bit more here. So let's say you had some big image. Repeat for all 3 cross 3s. Yeah, I mean not all. So what you try to do is there are some more factors that come into play. So this 3 cross 3 kernel I will try to put over this part first. Then I will get one number, right? Because I took the element wise multiplication and I added them all up. Okay, so I got one number from this. What I try to do is I don't put the next thing over here. I instead put it over here. So I moved only one cell to the right. Okay, I'm going to draw with other color, and then I move again one more cell to the right. Okay, is that making sense? Why are you doing such operation? Yeah, okay, so you will see that in general, if you wanted to the overlapping thing. Okay, so I will first cover what the, or maybe I should instead start with a 1D example. Are you familiar with moving average? Okay, so let's say you had a, we'll, instead of going to the 2D image, let's take an example of a signal. Okay, let's say you had some signal of this sort. Okay, and you wanted to make it smooth. Okay, since it is going up and down a lot here throughout the length, I don't like it. Let's say I want to make it smooth. Okay, one way I could do it is I will did I lose the connection at some point? Okay, I explained this part. Was that audible? The signal thing. Only the signal, yeah. So let's say I had a signal against time, and there was some value that I was measuring in this signal. So that value is jumping up and down. Okay, and that is what I ended up measuring. Okay, let's say this some noisy signal is there. I wanted to have something which is smoother, not jumping around like this. Okay, one way I could do that is I would, let's say, take the over a certain duration. Let's say I have the data set, so this entire thing is for, let's say, 10 time steps, or let's say 100. Okay, 10. let's say I'm collecting the data uh, at 1 hertz, which means I'm taking one measurement per second, and I have this data for 10 seconds. Okay. Uh, in that case, I would have 10 data points. Now, what I do is to get a smooth output from this, I take the average of all of these 10 values and only consider that as my signal. Okay, that would be one way of making it smooth, right? Is that making sense? But aren't we losing info? Correct. So as you can see, let's say my signal was not that kind of thing. Let's say it was something like that, and if I ended up taking a average of all of these guys, let's say maybe it goes something through like that, I totally lost the information that at these regions the signal value was a bit high, here it was a bit low, here again high, and here it is maybe achieving a mean value or something like that. I lost all of that info when I just took the average of the complete thing. Okay, but instead if I take, let's say, average of this much size of the data, okay, for this size I take the entire average, so let's say that average came over here, and then I took the average over another block of the same size, but I moved the entire so whatever this size was, let's say this was the 10 step size. If I moved 10 steps ahead and took average over there, I might get the average like this. Then I moved again 10 steps ahead and I'm over here, so I will take average of this part, it might be something like this, and then I went over here, took average of this, that might be somewhere here, and next 10 again here, then again here, and you get the idea, right? Yeah, looks like a step function. Yeah, so now my goal was actually to make it smooth, but I have not actually made it smooth. I have made it into some sort of a step like that. Okay, so how do we resolve this problem? So our goal was actually to make it smoother, right? So one way to do that is, instead of jumping 10 steps ahead, let's me jump only one step ahead. Okay, so what would happen? So only for the first data point I am considering this as the point. For the next thing, since the weightage, since there are a few data points that are down in the downward trend, I would end up going a bit down here. So for every step I'm taking, I'm getting out only one value. Losing network. Hello, am I audible? Yeah, can you tell me where you ended up missing? Yeah, my net connection is today bad here. Can you tell me at what point you missed? Hello? You can unmute yourself and talk also. That is not a problem. Oh no, my God. Okay. Okay, I will just. Okay, fine. So you saw, right? We were getting this. Oops. Whenever I put my hand, it goes. I will ask if any. Okay. So what was happening was I was getting these steps, right? But I wanted a smooth signal. So instead of jumping 10 steps ahead every time, I will only jump one step ahead. Okay. So I took average of next 10 steps. So from t equal to 0 to 10, I took the average of all of those, and I took that as my only the first value. But then I took from 1 to 11, and I took the average of those numbers, and that I put as my second index value. Okay. Then I did the same thing for the next. So I kept on shifting my window. So if I had to draw it, let's say the signal was something of this sort. I'm taking this much size of my this much size. I'll fix my step size basically. So there will be less change in average. Yeah, that's the entire idea. So if I take 10 steps and then moved over here and took another 10 steps, that would the smooth signal will end up becoming smoother. So it would not jump around too much. Yeah, and it would go something like that, right? So can you relate this, what I just said, to what we are doing over here? Okay, got it? Yeah. So in general, in case of moving averages, what you are doing is you are taking all of these, you are essentially multiplying all of these input values. They are being multiplied by 1 and then being added, right? So if I didn't do 1, instead if I multiplied with all of them with some factor, so a convolution operation the basic version of a convolution operation would be a moving average, but a more complicated version can also be made. So instead of taking all of them with equal weightage, if I have a weightage of this sort, and what are you getting what this would mean? So every time I'm moving my window, I'm giving more weightage to the values that are in the middle of the window. Okay. How would decide weights? Oh, we haven't got to that point yet. The thing is, I'm just still on the convolution operation. So a convolution operation in general for a 1D case would have something like this also. So instead of considering a 1 unit value to be multiplied with each of the input, each of the numbers on my input data, I can have a what do I say? This is actually called the kernel. So this is a kernel function sort of thing, or convolution function. The function to be convoluted using, like sigmoid. No, not sigmoid. Sigmoid is an activation function that has a different purpose. This is more like so if I choose this sort of a function to be multiplied throughout the signal, and I keep passing that over the entire signal, it will always prefer the middle elements of the so in a 10 sequence in 10 numbers of the input, I'm always preferring these numbers more than these numbers on the edges when I'm using a kernel of this sort. Okay, so you keep moving this in the window. So when I'm looking at another one more input, I'm taking the kernel and putting it over here. When I'm moving a little ahead, I'm putting the kernel like this. Okay, so that is what is going to happen. Ideally this could be any function. I could even choose something like a box, so that would only take the average using these middle elements, and it will totally zero the side ones. And so our actual goal is what I just described. That is so this is a different type of functions. Are you getting that idea? So this was a unit value function, let's say. This was something like a Gaussian function, maybe, or some sinusoidal function. Okay, so this function that I'm talking about, that I'm going to have the window to behave like, so the window function, I would just rather call it window function. The function that is moving over my entire signal, that could be anything, and choosing a different function would give me a different output, right? Are you getting that idea? Missed the last point. Okay, so when I was doing the moving average, I'm taking this as my window function, which is a unit value. So I'm multiplying each of these inputs. So this. So these are my the values of my signal, right? So I'm multiplying each of them with 1 and then adding them up. If instead I had a function which if I had a function of this sort, okay, what I would do is these middle ones, this one, so these are going to get a bit higher weightage because these values are bigger. Are you getting that? Yeah. So, and the side ones are going to get a little lower weightage, right? Is that clear? Yeah. So choosing a different function will ensure me that I will get a different sort of a behavior on the output. Okay, so now my goal has probably changed. Different smoothing effects, correct? Exactly. So choosing a different function, I will get a different type of smoothing effect, and depending on my function, the output will look something different. Yeah. So what I essentially want to do is, so now since I have chosen this red thing as a function, or I've drawn over top of it in green, this has some parameters, right? I mean, whatever this shape might be, this shape has a set of numbers that are defining that shape. So there might be something sort of a variance of this or a mean of this. So instead of keeping the mean at the center, I could have also kept something like that, right? So this function that I am using for window as a window, moving window, is actually called a kernel function. I will start using the term kernel. So this function has some parameters. So something is defining this function shape. I can vary those parameters and change my function also. Is that part making sense? Huh. So essentially that is what we are doing over here. These numbers, they are the parameters, and that is changing the kernel, the function that I am going to use to put over the image. Okay. Okay. So now what you saw, all of that was for 1D case. The same thing if you do in 2D case, you will get smoothing effects over the entire image in both the dimensions, and you will get different patterns, right? Thank you. Is that idea making sense? You will get different smoothing patterns in both the height, along the height and width of the image. Okay. So essentially that is what a convolution operation really does, and you will see that once you have done the smoothing, you can kind of, so this is actually a common procedure that they do. So let's say after smoothing I got another image on top of this. So this is not the original image, okay? This is after doing that smoothing, kernel, passing the kernel over the entire thing, okay? So whatever I got now, I can do something like a pooling operation. So there is something called a pooling operation. What it does is, it will take the maximum. There is two types of poolings commonly used. There is something called max pooling and average pooling. So this average pooling is more like your moving average that I just showed above. The previous thing that I all talked about was the convolution operation, and this average pooling, what that is going to do is, but this pooling operation is actually the one that is going to reduce the size. So let's say my image, this input image, which was this white thing. So my input image, let's say it was 100 cross 100. Once it has gone through this kernel procedure, let's say it's still for now, for just the sake of it, assume that it still is 100 cross 100, okay? And I used a 2 cross 2 pooling, okay? So what this 2 cross 2 pooling is going to do is, it will take this 2 cross 2 element. If I'm doing, let's say, average pooling, it's going to take average of all of these numbers and put that as my first number of the output. In case of pooling, I'm doing a thing that I'm not concerned with the smoothing operation, because I have already smoothed it, okay? I'm concerned with making the size of this image smaller. So size of this input, I want to make it smaller, because I have probably captured something using this kernel function, okay? We will come to the capturing part and all of that later, but for now consider this pooling operation. Okay, So in pooling operation, I'm not going to move just one step ahead. I'm going to move the same size as my pooling kernel. Okay. So if I have a 2 cross 2 pooling kernel, I'm going to move 2 steps ahead, and I'm going to keep on doing that. So can you guess what the size of the output will be after the pooling operation has been done? (25 cross 25) No. Why would it be 25 cross 25? I'm actually jumping out. So if you go look at along length, I'm only combining 2 of them to get 1, right? So every 2 went to 1, and same thing along the height. Yeah, so 50 cross 50. Yeah, right. So what you ended up doing in this entire procedure that I just described, so you first had the input image, this 100 cross 100 input image. You applied a kernel function on top of it. You got this green thing, okay, which was a sort of a smoothened effect of this input image. Then I took this pooling operation, and here is where I made the input size smaller. Okay, so new number of inputs is less. Yes, exactly. And I keep on doing this procedure. So on this 50-50, I will again do a convolution operation. So maybe I have again 3 cross 3 kernels being put on top of this 50 cross 50. Let's say I manage to get again 50 cross 50 input after this entire procedure has been done. I will again do a pooling operation. Let's say again for 2 cross 2, I might get a 25 cross 25. Are you seeing how this can help you reduce the size? Till when? Exactly, good question. So what I have been describing till now, it was only using one kernel, right? Here you used only this kernel, and you got one output. Okay, so I'll start drawing the main CNN diagram there. So let's say you have a input grayscale image of 100 cross 100. You do a convolution operation of a 3 cross 3 kernel. Okay, so when you say 3 cross 3, okay, you don't choose just one 3 cross 3 kernel. Okay, you choose multiple of those, and each one of them will have different numbers in this. This actually corresponds to different types of these functions that I talked about. So you can either take this step kind of thing, you can take a sinusoid kind of thing, you can take this shifted peak thing, beta function kind of thing, different smoothing. Yeah, so you keep on doing different type of smoothing. Each smoothing will give you 100 cross 100 output, right? But you can have a bunch of those for corresponding to different smoothing effects. Are you getting that? Yeah. So output after my convolution layer is not actually just another 100 cross 100. It's actually 100 cross 100 cross number of, it's like a cube now. It's a 3-dimensional output that I'm getting. So let's say I used C number of kernels. I'm going to get C number of these layers. yeah, number of kernels, that many number of 100 cross 100 things I'm going to get. Are you getting that? Yeah. So now you might say I actually increased the size of the thing, right? So yeah, huge. Yeah, it is a huge computation, yes. But uh, you you might say I increased the number of I mean I started with 100 cross 100, but I ended up getting 100 cross C. So I actually ended up increasing my size of my input. But after this, your pooling operation will come, and that will make it 50 cross 50 cross C. Okay. So once this 50 cross 50 cross C is, so again I will send this as input, but this time when through convolution. Okay. So I'm again going to do convolution of size 3 cross 3, but this time my kernels are not 2D, they are 3D kernels. It's going to move like that. So this whatever I'm drawing, my kernel is a 3D block. Are you getting that? Yeah. Step 1 2D kernel. Yeah, because my input was a like a this grayscale image. If my input itself was a 3D, I mean RGB image, I would have started with doing 3D kernel from the start itself. Okay. So since I started with a 2D image, I first applied a 2D kernel, and later my input became 3D, so I started applying 3D kernels. Okay. So once I've done this, let's say I still managed to get 50 cross 50, and so again when I'm doing this, the size of each of the kernels was 3 cross 3 cross C, but I can still choose a different variety of these kernels, right? So after the first thing, let's say I choose C1 number of kernels. If later I choose C2 number of kernels as, so C2 number of these variants, my output is going to be 50 cross 50 cross C2. Is that making sense? Okay, so the first time around I had C1 number of these 3 cross 3 kernels, right? Is that getting clear? That C itself, I'm just calling it C1. One for each. Yeah, I mean, so each of the layers of this or slices of this, they are coming from a different kernel. Yeah, so I had, let's say, C1 number of such kernels. So in the first step I had C1 number. Okay, I'm saying now that in the second step I have C2 number of kernels. Okay, yeah, that's all. But each of these C2 number of kernels, they are 3D volumes, 3 cross 3 cross C1 size. Okay. That's the idea. I mean, is that making sense? 3 cross C cross C1. Got it. Okay, good. So each of these 3 cross 3 cross C1, when they run over the entirety of this 50 cross 50 cross C1 input, they will give me one layer. Same as above, same as the previous procedure that we did. Okay, so when I run this over the entire thing, maybe I should draw this a bit more. So 50 cross 50 cross C1, I took a kernel like this, so it was overlapping on a 3 cross 3 region here. Is that making sense? Yeah. So I keep moving this block sideways. Okay, I keep moving sideways and down, and every time I'm going to take sum over the entire thing. Whatever it is overlapping on my input, I'm going to sum over that entire thing. So this is actually called volumetric convolution. Because the input was a volume, I'm now taking sum over the entire thing, that is volumetric convolution. Are you getting that idea? Yeah. Now, since you have to take volumetric, your kernel itself is having 3 into 3 into C1 number of values. So along each of the layers of this kernel, the values are not same 3 cross 3. They are different 3 cross 3 because it's a different function, right? Each of the different layers denotes something different. They came from a different kernel. So I should have not C1 values, 3 cross 3 cross C1 values. So 3 into 3 into C1. Okay. So each of the kernels that I am having for the next procedure has 3 into 3 into C1 number of parameters. Okay. And I am having C2 such kernels. That's why. So once I pass this entire thing, this 3 cross 3 cross C1 kernel over the entire input, I will get one bread slice. Okay. So this is from my first 3 cross 3 cross C1 kernel. So first kernel of my this second convolution process, such C2 slices, exactly. Good, my life, you are making my life easier. Yeah, such C2 slices. Okay. And again you do pooling operation. You can make it half and you will get 25 cross 25 cross C2. Okay. Is that clear? So here I did pooling. So now I can keep doing this procedure. The thing that they do when they are implementing these convolutions is that usually this C1 number is going to be less than C2. Okay, so I am going to put more number of these such kernels, 3 cross C1 kernels, than they were in the previous layer. I mean, that is to get a more, you can say, in fact, that will come later. We'll come to that main point later. Why we keep on increasing the number of. So as you can see, we are reducing the number of dimension in this length and breadth, right, of the image. With every successive convolution and then pooling, you are reducing the size of the dimensions that were present in the original image. So width and height of the image is now shrinking. Is that making sense? Yeah. But if you keep on increasing the depth, okay, you keep on doing this procedure until there comes a time when you have only a 1 cross 1 and n number of features. Are you getting this? Okay. So this entire procedure that we described just now, you keep on repeating it until you have a 1 cross 1 cross n, and this n is now a big number, quite a big number. So let's say in the starting few C1, let's say it was a few, maybe 10, let's say, and maybe C2 was some hundreds. You might, by the end in n, you might go to thousands or thousands, something like that. Okay. So now, after this point, I can essentially stack them all up. Can you describe n again? Okay. So this procedure you got, this procedure. Yeah. So I will keep on repeating this sort of a procedure till I get a 1 cross 1 cross n. So I'm reducing the size along the height and width, but I'm increasing the size along the depth. Okay. Is that making sense? So at one point I will have this 1 cross 1 cross n. This 1 cross 1 cross n is essentially n numbers, right? Is that making sense? What is it? Okay, for now just consider them as n numbers. They are just n numbers. N number of, so n is actually the integer. N is equal to 1000 in this case, let's say. Okay. So I have 1000 such numbers. What I can do now is I will put these 1000 numbers and put a classical neural network after this to classify my, so do some classification task. Okay, so this was 1000, and let's say I wanted to classify into, so I thought n is equal to 100 cross 100. No, n is not that 100. No, it's not that. In fact, that was what that is what the entire procedure achieved. So this 100 cross 100 image, which was 10,000 numbers, we, in some sort of a way, we through this entire procedure, we boiled them down and got them less to a fewer number of numbers. So that entire image, whatever it was representing, you ended up capturing all of that into a smaller 1D vector. That is what we achieved through this procedure. Okay, so when I said 1000, it could be, it is not necessary. It could be even 512, and there are different models that have this. This number will be different for different models. Okay. So, but for different variants of CNNs, I would recommend you to go through the week's content, because I can't cover that, all of that. But this is more like the starting steps. Okay. So, I mean, that is the entire architecture of a CNN. So once you have boiled down the entire 100 cross 100 image into this 10,000 features, so you have essentially boiled it down to a 10 these 1,000 numbers, which in reality they don't uh, particularly relate to anything in the image. There are some weird dimensional representation, some, you know, uh, I mean, we can't interpret it, but in some dimension, this 1,000 dimensional space, it encodes whatever was present in that image. Okay. Yeah, that's all. And this 1,000 cross 100, let's say you have 10 classes to be classified into, you'll put a fully connected layer over here, and this you can have the here softmax can be applied for you to classify and get probabilities of this belonging to each of the classes. That's the entire architecture of a CNN. Teddy? Okay, yeah. So that's a very brief overview. I mean, I would still recommend you to go through the entire lectures. That would give you in much detail. Okay. So we are now left with only half an hour. But yeah, I will just complete the question that I started with. No problem, no problem. We started with the question of batch normalization. Where is it? Yeah. So we wanted to talk about batch normalization for CNN. So in case of CNN, one way of doing a batch normalization would have been, so let's say my data set had 30,000 images, okay, and I grouped them into batches of 30. Okay, one way, so each of these 30 images, let's say they are, for now, for the sake of this example, let's assume that they are grayscale only. Okay, so one way of doing batch normalization could be, I will look at what is the pixel value at the top left corner in each of the 30 images and take a mean of over those and put that as my mu, the mean. And I will, so my mu, the mean itself will be, so let's say these are 100 cross 100 images. My mean itself will be 100 cross 100. Okay. So over a batch of 30 images, my mean is 100 cross 100 size, and so I'm subtracting a sort of a mean image from each of the images of that batch when I'm doing this x minus mu by sigma square. Okay, is that part making sense? That is one way of doing it, but that is not the correct way to do it. We'll come to why. Okay, so that is one way of doing it, but in CNNs you don't do it like this. What you do is, since you are saying that we are passing this entire kernel over the this entire image, right? What you should ideally be taking the batch norm over is not actually the I mean, this doesn't suffice here because it's a 1D. Maybe I should talk over on this thing. Okay, so let's talk over C1 to C2 normalization. Okay, and my batch is still of size 30. Okay, so I have 100 cross 100 cross C1, such 30 of them. Okay, is that making sense? So I'm talking about the, after the first convolution, I'm going to the next convolution. Whatever was my output after that first convolution, which was a 100 cross 100 cross C1, right? So this 100 cross 100 cross C1, I had 30 such things corresponding to each of the input images. Is that making sense? So after doing the first convolution operation for each of them, okay, now I want to start doing the second convolution operation. Before that, I'm not going to take, let's say, so if I wanted to do the traditional batch normalization like this, what I described here, my mu itself would also be 100 cross 100 cross C1, the traditional way. But instead of doing it this way, we actually do the normalization. So the average that we are going to take is actually going to be the over the entire this layer for all of them, all 30 of them. Now you might ask, why are we doing like this? So for now, let's assume that you did do that. So you took average of this entire slice, average of this entire slice, this entire slice, this entire slice. So whatever is the average of all those elements, and so this would result you in some C1 number of numbers, right? C1 number of averages. This would also result you in C1 number of averages. This would also result in C1 number of averages, right? 30 into C1 total, yes. So now I have 30 numbers for each of the images. I'm going to take the first number of each of them, and that I'm going to use as the first mu. And like this, I'm going to take mean over the. So my mu is now going to be only 30 numbers. No, sorry, not 30. This size, the C1 size. So there are 30 into C1 numbers here, but I'm taking mean of these numbers. So I will have C1 such numbers. Okay. So my mu, the mean actually consists of C1 numbers. C1 means, yes. Okay. So you might ask, why did we do that? So this way you would have had a lot more number of means over X here actually. So if you had done for this thing, it would have been 100 cross 100 cross C1. Okay. But instead we chose to do this sort of thing. The reason for that is actually because of something called weight sharing. So all of these 30 images, they are going to be going through a kernel. No, it won't be same. I mean, here I have 100 cross 100 cross C1 numbers as the mean. Here I have only C1 numbers as the mean. That's a very different vector, right? I mean, this is a volume, this is a vector. Is that making sense? Okay. So, what was I? So the reason why we are doing this sort of a mean is actually because all of these, so each of these first phases, they are going to go through a particular kernel, and they are going to go through the same kernel Are you getting that? So all of these, the first phase of the inputs for each of the images, they are going to go through same sort of weight multiplications. No, not all C1s. My kernel at this point is going to be 3 cross 3 cross C1 dimensional. But the first phase of my kernel is going to get applied to the first phase of each of these 30 images. The second phase of my kernel is going to get applied to second phase of each of these images, and the third phase is going to get applied to third. So all these C1 number of phases of my kernel, which is this 3 cross 3 volume, they are going to get applied to each of these phases of my input. So are you seeing that? So this W transpose X that I was doing, so this, when it passes over the first thing, that is going to create one input neuron, sort of like that. That is actually acting as a, so in what I actually want to try to convey is that in case of a CNN, a kernel is a function, kernel is a feature. First 3 cross 3 for first phase, like this C1 phases, correct, exactly. So my mean, it makes sense that I use such C1 means only, rather than, because this entire phase is going to go over the entire this entire phase, right, of my input. As it is going to go through it, it's going to scale the weights with this, its input numbers, whatever these numbers are, it's going to scale all of these numbers with those. That's the idea. So that is the difference between using a batch normalization for a C1 kernel. Yeah, because my kernel is C1 sized, C1 depth. That's the idea. Yeah, C1 number of kernels. Yeah. Okay. Oof. I'll drink some water. Okay, so that covers the question that we started at the start. If anyone has any doubts about what I've covered so far, let me know. We covered a lot of content. How do you visualize it? Visualize what? This entire procedure. I mean, so the thing is going to be that we need to write code for it. So if you can go through my previous last week's lectures, I have actually demonstrated the codes for implementations of CNNs. So maybe I will, should I share the link? I think that would be a good idea. So you can click on this link and it will lead you to a playlist. So last two videos of that playlist were both about convolution neural networks. So I showed using the PyTorch library how you implement a convolution neural network. And I would recommend you to first go through the NPTEL lectures that sir has taught, and then you come to these videos, because a lot of elements in this was based on those as the background. Yeah. So this is the main idea of convolutions. That yeah. So last 2 weeks were all about convolutions. Today actually I was going to show the demonstration of the next set of architectures, which was the RNN and LSTM. But I think we still have 15 minutes. If you want, I will just breeze through the code. Is that okay? Yeah. Is my code scene visible? Okay. Is the font on it okay, or should I zoom a bit? Yeah, now it looks okay, I think. Is it okay? Okay. So I actually wanted to show a demonstration of something called image captioning. So what that essentially means is that if I'm given an image, can I train a network to make a caption for it? So describe what is going on in that image. Okay. So that is what you can achieve with a mix of convolutions and these RNN LSTMs. Okay. So after you complete the convolutions, the week 6 and 7, in the week 8 you will see all about these RNN and LSTM architectures, which are basically for sequence to sequence modeling. So if I send in an input as a sequence, I can get output as a sequence, and it's very important for various NLP related, so natural language processing, your ChatGPT, all of those, they are based on these ideas. Right? They are based on much advanced ideas than this, but that's the general idea behind it. Okay. So I've given a link. I'm planning to, when I share this video, I will put the link to this Colab Notebook in the description of that video, so you can later go and check that thing also. So here I have made a big note here that the goal of training an image captioning model is actually for our model to learn the association between the features in the image to the words. So a caption is essentially something in words we are describing what is in that image. But let's say there is a maybe we'll go through some examples. So the data set that I've chosen, let's say this particular image. So the caption for this is a young child eats a small cake. Okay. So in this image, your model needs to understand what part of this image is actually denoting the cake and what part is denoting the child. Okay. So that association it needs to make. So that is the general idea of these image captioning tasks. Is that making sense? Okay, for example, even here, It says 4 dark-skinned men with no shirts are working in a field with a cart and several cows. So now the model needs to understand what in this is cows, what is this means field, what in this means people, all of that. Okay. So the association is what our model needs to learn. Since this is actually going to be a very, actually the entire session I would have needed for explaining what is going on in this code. So I will only briefly tell what is going on. So we are using this Flickr 30K data set. Okay. So this data set has 30,000 images, or more than 30,000 almost, and each of them is captioned. So what you saw here is actually examples from this data set. So some images will be there and some caption of it. So this caption is given by a human. So a human made this caption, and that is our training data set. Okay. So in this particular data set, they actually give 5 captions for each image. Okay. So 5 different people must have labeled what is going on in this image, and based on that, you will feed all of that information to your model, and the model will try to find the association of different elements of the image to the words. Okay. So I'll maybe describe only a rough overview of what each of the code blocks is doing. So here I'm just importing some libraries that are required for this code. Yeah, here all this is doing is, let's say I'm given this sentence, this is a good place to find a city. I need to separate all the words or things in this present in this sentence. So that is called a tokenization operation. So I'm putting, so all of this have become a separate word. So this is a good place to find a city, like that. Okay, that is all this is showing. Then this is all of this, what this block is doing is creating something called a vocabulary. So in general, the English language will have many words, right? I can't expect so I don't want the association between all the words in the English language being associated to whatever is present in my data set. I want only the captions. So the captions are already having a certain number of English words. I want them being associated to my images. Okay, so that is what we achieve with this vocabulary class. And to make our life or to make the process of interpreting or the running of this model easy, we do something called this process. So if I have these several words, this is a good place, all of these are separate words, I can't put this and send it to a neural network model, right? I need to send it numbers. So what I will do is I will map these words to certain indices. Okay, and I will create a vocabulary. So I will create my own dictionary which has only that many number of words which my caption has. So I have, let's say, 30,000 images. Each of these 30,000 images have their own captions, and whatever words are present in that entire caption, I will create a vocabulary of that sort. So my vocabulary obtained from here is actually a subset of the English language vocabulary. Is that part getting? Yeah. So that is the entire idea over here, and there are some special characters in this to denote. So I will put start of sequence and end of sequence in front of each of my captions in the data set, so that I will know where the caption started, where it ended. And I will also have a special character for padding and another character for unknown. So if there is something, let's say if my caption in general, so let's say my caption had a emoji, and I don't want, in my dictionary I don't have the way to represent that emoji, so I would replace that with this unknown. So because I don't want to include that emoji description in my caption. I mean, you can include if you are trying to do a very advanced version of this, but for a simplified version we are not including that. Okay, so I will not go to all the details here, but that's the general idea. So this vocabulary is building a subset dictionary of the words from the captions. Okay, and yeah, this is how it will look like. So if I send this sentence and try to build vocabulary only using this sentence, that would look something like this. So in my vocabulary, this particular symbol, this pad, is denoted by 0, and I've mapped it to indices, as I said. So because I need to tell my neural network model or the machine learning algorithm, I can't feed it words, so I need to feed it numbers. So the mapping of the words and the numbers is happening like this. So this particular this as a word is being mapped to number 4. Is as a word is mapped to number 5. A is mapped to 6. New to 7, and so on. Okay. That is all that is happening over here. Then this is something called a data loader. So what I described when we were going through that batch normalization and stuff, we don't want to load the entire data set at once into our RAM. So in fact, when I was trying to run this particular model in my laptop, initially it crashed my laptop, because my laptop was not able to handle so much of data at once in its RAM. But now I'm showing it on a different system. So in general, this is what you will always do. So you will try to get your data and put it into batches. Okay, and the way you load is using something called this data loader. So in PyTorch, this particular thing is implemented as like this. So the way this works is that you will send it the directory, so where all my images are being stored, that path I will tell. I will also tell where my captions are being stored, that file wherever my captions are stored. And this data set loader, this function, it will at a time take 32, let's say if my batch size is 32, it will take 32 of the paths from this directory and only take those and load them into my RAM. Are you getting that? How it is achieving the batch, right? So at a time it is loading only a less number of images, and their corresponding captions are also being called from the way that data set is organized. You can get that. Okay. So that is all this thing is about. So this entire thing will make your data set loader. Okay. Then this part is actually for where is the batch size mentioned? I will mention it later in the code. I'm only defining the functions. Okay. So yeah, coming to this block, this block is going to, so let's say for I have 32 images in a batch. One of the images has a caption of 40 words, let's say, but some other image has a caption of only 10 words. So if I'm using that in my network, uh, I mean it can't take 10 and then 40 and uh, I mean it can't decide that I need to predict 10 once, I need to predict 40 in other case, and so on. So to get the same number of predictions as the size of my feature vector, the output vector, should be same for all the elements in that batch. To achieve that, I'm going to pad each of the captions in my dataset to the maximum number. So I will take a particular batch. In that, let's say the maximum number of words in a particular caption were 40. That 10 number of, so there was another caption which had only 10 words. I'll put 30 zeros after it to make that also 40. Is that making sense? Okay, so I'm making all of them. Essentially, that is what I've written over here. So I'm padding the captions such that they match the largest caption in the batch, and that is what is achieved with this block. This is a function to just show an image along with its caption, and here is where I have mentioned the batch size. Okay, so I have 32 images in a batch, and this dataset has around 30,000 images, so I will have 1,000 such batches. Okay. And as I said, I need to specify the path to the folder of images and captions. And yeah, here is where we created that data loader object using this. So this Flickr dataset will be used here. So this. Okay. So basically this is only for the loading work, and this you can see this cap collat. So appending or putting those padding on all of those captions, that is also sent in as a function to this. Okay, to this data loader. So whenever I call a batch, it will automatically put this function on the captions. Okay, so that is what is going on in this entire block. So this block is just for you to see what is happening. So using this thing, I am taking only one of the batches with this thing, and I'm showing you what all is present in that batch. So all of these images that you are seeing with their captions, they are belonging to one batch. So this particular image has a bike rider. So this bike rider is jumping high over a dirt hill and seems to be higher than an electric pole. So different people must have put these captions in different ways. So they must have decided to look at different things in the image, and depending on that, they have described the images. So as you can see, there are a variety of images here. Okay. Yeah, here is where we are actually defining our model. Okay. So this is going to be a bit difficult to explain, but yeah, in this model, what you are essentially trying to do is you have been given an image, but the output you want is the sequence of words, right? So the process of so there is a class of models called encoder decoder models, and in fact, this particular thing is called an encoder decoder architecture. Okay, so what an encoder means is that your input, whatever is the input, it will be uh, shrunk down or made smaller into a smaller set, smaller feature size, and that small feature size will be then expanded or decoded into another form. That is what an encoder decoder architecture is all about. Okay, very simply. So here we have a CNN architecture as our encoder, and I'm using here the ResNet model. So this is actually described in the week 6 content. So I'm using that as a pre-trained weights from that model. You can go and look at the pre-training and all of that stuff. Okay, but for now just know that I'm using the CNN algorithm architecture, that all that we studied today, that I'm using as my encoder, and I can get a shrunk down version of that entire image, and I'm using the LSTM model as my decoder. Okay, and this is a function called generate captions, which will, after my entire process has been done, I'm going to call this. So this function is not going to be used while I'm training, but it's only going to be used when I generate the captions finally. Okay, we can't go through the architecture of LSTM now, but just know that with this part of the code, we are achieving from that simplified version, what you encoded from a CNN, you are decoding using an RNN. Okay, is that okay? And I'm collating all of that together into this encoder decoder class. So this is going to call my encoder CNN and decoder RNN. Okay, and I'll just briefly tell this part also. So in general, you must have heard that we use GPUs for training, right? So in PyTorch, the library that all of this code is written using, so you can actually achieve this using this. So this will ensure that it will check basically whether your device has a GPU or not, and it will print CUDA if your device does have a GPU, and it will print CPU if your device doesn't have a GPU. Okay, so this is a standard thing that people do. Okay, and you would actually want to do this because what is the significance of using GPU? Okay, so in general, whenever you are training these neural network models, you want to parallelize the computation. A GPU will make that happen and make your training procedure a lot faster than what a CPU can do. CPU will do a sequential process. It might not, depending on the number of cores you have, you can only go that many number of sequential tasks that can go happen. But in a GPU, everything will happen parallelly, and you can do, basically a GPU will help you do these matrix multiplication sort of operations very fast. Okay, and here are some more hyperparameters related to this model. And these are some functions that are going to be used in this thing. So I'm defining the model as this encoder decoder model. So I defined the class over here. I'm creating an object of that class over here and calling it model. And then I'm using this cross entropy as my loss function because so whatever my output comes out to be, I actually want to check whether so I don't care whether my caption really has in the same order, the words in the same order. I just want to see whether they are present or not. Okay, so in this particular model we are implementing it like that. in general you would want it to be with the proper grammar and all, and that will take a lot more training and better architecture. But for this particular simple example, we don't care about the order. Okay, but you'll see the model still learns some of that eventually. And then the loss or the optimizer, we are using this Adam optimizer. Okay. So this is the main training procedure of the entire model, and I will just briefly run through the, instead of showing the detailed code, I will just briefly run through how the model was training. So at the start, I ran the entire thing for 20 epochs. Okay, and you'll see that in the start the model was very bad in doing its captioning task. So it is in fact putting all the time it is putting this same caption. So a man in blue shirt is standing on street. In fact, it is keeping that as the same caption for a long time. But eventually, let's say this is still in epoch 1. As we go down, let's say around somewhere in around 10 epochs. Yeah, let's say this particular thing. So around 7 epochs, it is starting to do a bit better job. It has, in Colab, do you mention how many CPU, GPU you need for training? In general, yes, you can specify that. But Colab, I think it allows, it has some restrictions on how much you can actually use. But this particular model that all of this that you are seeing, I didn't run it on Colab. In fact, if I had run it on Colab, it would have taken way longer. I'm running it on my local system. That's why here at the top you will see connected to local. In fact, that is the thing. If any of you guys eventually later try to train this, if you try to train it on Colab, it will take very long. If you have GPU on your system, you can use that. Okay. So, yeah, coming to the, yeah, you can leave it overnight, yeah, but Colab also doesn't allow you to do that. It will expect you to keep the screen active often. All the problems related to free usage, I guess. So at around 7th epoch, it's doing a bit better job in captioning. Somewhat okay, still not very good, but this set did a bit better. So for different examples, you are seeing what it is able to do. So it is still messing up on a lot, but here at least it had an understanding that what a riding a bike part of the image actually refers to. Okay, so this, as I said at the start, your ultimate goal with image captioning is to find these associations between whatever is present in the image and what to put in the text as the caption. Coming down, we'll go much down. So even here I trained only for 20 epochs. It can go higher also. Ideally it would better go higher if you want better results. So let's say around 16th epoch, did quite a bit better job, right? Yeah, this is what you would even we would put as a caption. Here it's not really understanding what an orange really means, but it put the riding the motorcycle part correctly. Okay. So eventually, as you train it for more number of, I mean, a lot more number of epochs, and even in fact, you can go on a better architecture also. Whatever I've described is probably not a very good architecture to do this, but there might be better ways. So you can make it more complex models to better feature. I understand. Architecture, yeah. I mean, I kind of skipped that part a little bit because it would take a long time to cover that. You need to go through the lectures of week 6, 7, and 8 to really understand this architecture. Okay. Yeah. So actually, that is what I was trying to achieve with these weekly sessions. So every week I try to bring a actual example of you done through coding on whatever you learn in that week's content. In last week's content, I showed two applications of convolution neural networks. One was related to denoising of images. So if I have so I showed it on a demo data set of these handwritten digits, and I added some noise on top of it, and you can actually get a clearer image from that from the noisy image. You can get out the clear image. So that demo is what I showed in the last week's video. The YouTube link that I shared, you can go through that, yeah. But after you watch the week's videos, okay, yeah. So, I mean, after the week 8 thing, you can actually understand most of this code also then. So what LSTM means and all of that you will know. Okay. So I think that would be a brief summary of this thing. Okay. So when we'll meet next? Yeah, this session I take every Monday. So every Monday 6 to 8 I'll be taking this session. For all the previous sessions you might go through that playlist that I from that video I shared. Next week I will cover whatever is in week 9's content. Yeah. So go through the week 9's videos, and based on that I will cover something. Okay. So I think we will stop for today. Yeah, thank you. Okay, so we'll close this session for today. Okay. Do attend the next session also. But today there was a way too little attendance. I think the maximum attendance today was around 3. 3 apart from me. Yeah. Thank you for attending. Because at least you two guys attended, I was ready to cover this thing. Else my all the preparation goes waste, right? Okay. So we'll close the session for today. Yeah. Meet you guys next time. Chalo, bye.